there is so much to unpack with this new image of the Milky Way's supermassive black hole. Like, why is it orange, and why is it so blurry, and what are the three blobs, and how does it compare to the first ever image of a black hole we had in Messier 87 as well, and what angle are we even viewing this from? So let's dive into this. Yesterday, on the 12th of May 2022, the Event Horizon Telescope released this image of the supermassive black hole at the center of our galaxy, the Milky Way. It's known as Sagittarius A star because the center of the galaxy is in the same direction as the constellation Sagittarius on the sky. And in the past, zooming into that region of the sky, all we've ever seen is this unresolved blurry blob. But now, the material orbiting close into the black hole has finally been resolved with all of this detail. You can see this bright ring of radio light from the material orbiting the black hole, and you can see the shadow of the black hole where we're no longer receiving any lights. To get an image like that, zooming in that far, you need a really big telescope. And the Event Horizon Telescope essentially combines a whole bunch of telescopes around the Earth to create effectively a telescope that is the size of the Earth. Because the bigger the telescope, the smaller the thing you can see on the sky, the more you can zoom in. Because even though the Milky Way supermassive black hole is 4 million times the mass of the sun, the actual diameter or the size of the event horizon, that region that we're no longer getting any light from, appears to be about the size of Mercury's orbit, 116 million kilometers across. Which sounds big, but the center of the Milky Way is also 27,000 light years away from us. So it took light traveling at 300 million meters a second, 27,000 years to get from there to here. And so it actually appears really small on the sky. If you think of the sky of being 360 degrees all the way around, then this thing only spans a distance of 0.0000001 degrees. Now, this thing looks like a big orange donut, right? This big ring of material. And so the best analogy I've heard to describe, how small that would actually appear is it would be like seeing a donut on the surface of the moon. But also, this thing is only about 100 times brighter than the sun, which might sound bright, but that's pretty faint for material spiraling around a black hole. And combine that with the distance it's at, it's even fainter still. So to actually detect this, you have to combine lots of different telescopes from around the world in a process known as interferometry. You can think of this as if the Earth is a disco ball, with each bit of mirror of the disco ball a telescope looking up at the sky to see this one big image. Now, unfortunately, we don't have a telescope at each of these locations on Earth, though there are gaps in the disco ball of this array of telescopes. But as the Earth rotates, this then fills in some of the gaps in the picture. But as you can see, it's not all the gaps that get filled in. So the collaboration at the Event Horizon Telescope actually had to develop this brand new computer algorithm, a machine learning algorithm that could fill in the gaps using images that we've seen before of other completely different things to find the most likely image of what it would like given the bits of data that we do have. Katie Borman, who's a computer scientist on the Event Horizon collaboration team, has given a great TED talk on this before if you want to know more about how this algorithm actually works. I'll link it in the video description down below. Now, this was the exact same process as was used to image the supermassive black hole in the center of the galaxy Messier 87. Now, the observations of both M87 star and Sagittarius A star were done with the Event Horizon Telescope around about the same time, in April and November of 2017. But it was the image of M87's black hole that was released first way back in 2019. And that surprised a lot of people because I think people thought that, we'd get the image of Sagittarius A star first since it is the closest of the two black holes to us. But the thing is, Messier 87's black hole is 1,000 times more massive than the Milky Way's black hole, which means that its diameter, its event horizon, is also 1,000 times bigger. But get this, M87's black hole is 1,000 times further away from us than Sagittarius A star is, which means they actually appear roughly the same size on the sky. In the same way that the moon is roughly 400 times smaller than the sun, but it's 400 times closer to Earth, so it appears the same size in the sky, and this is why we can actually see total solar eclipses where the moon fully blocks the sun. So when we compare these two images side by side, we have to remember that in reality, Sagittarius A star is way, way smaller than M87 star. And while the whole solar system can fit inside the black hole shadow of M87 star, not even the orbit of Mercury fits inside the black hole shadow of Sagittarius A star. And yet the two images look remarkably similar. So what that tells us is that despite these two black holes being in two completely different types of galaxies with two completely different galaxy masses, is that up close to the event horizon, they behave in exactly the same way. So any differences that we see far away from the black hole, like for example the M87 has these huge jets that are launched from the surrounding regions of the black hole, that's all to do with the material that the galaxy pumps into those regions around the black hole, not the properties of the black hole itself, which is a really cool result and has really big implications for just galaxy evolution as a whole, and especially my research where I look at this co-evolution of galaxies and their supermassive black holes together. Now, the other thing you might have noticed comparing these two is that the Sagittarius A star image is a lot blurrier than the M87 star image. And that actually comes down to the fact that these things are actually quite faint by the time the light reaches us. So to collect enough light to build up an image, we actually have to observe them for a really long time, like hours at a time in a single night. But the material that's orbiting and looping around the black hole that's glowing and giving off that radio light that we actually detect is moving close to the speed of light. And so it loops around the fairly small Sagittarius A star in just a couple of minutes, which means that as you stare at it for hours, it's constantly changing and you essentially get like movement blur on your image. Whereas M87's black hole is 1,000 times wider, and so even though the material is moving at close to the speed of light, it takes a couple of weeks to fully orbit that black hole, which means that as you stare at it for a number of hours, material doesn't look to actually move that much, and so you get a much crisper, clearer, static image. So that meant it was much easier to analyze and construct that image of M87 star from the data that they had because it was static, whereas for Sagittarius A star, they had to develop this new sophisticated computer algorithm that could actually account for the movement blur in the image. The other problem is that when we look towards M87, we're looking up and out of the galaxy, and there's nothing really in our way spoiling the view. Whereas when we look towards the center of our galaxy, we're actually looking through a huge amount of dust and ionized gas, all of which has an effect on the light heading our way. For example, optical light gets completely absorbed by dust, which is why you see these darker patches in the sky at night in the Milky Way. But radio light actually gets scattered by free electrons in gas that's between us on Earth and the center of the Milky Way, which means that light from this already very faint object, we're losing some of it thanks to the scattering, but also some of it will just change direction slightly as well. So it'll appear as if it's come from one part of this ring of light around the black hole, but actually it's come from a slightly different part. It's just been scattered to look like it's come from a different direction. So that, combined with the fact that your image isn't static, you've got all of this movement happening all the time, made analyzing, constructing this image so much more difficult. 3 extra years in a pandemic, difficult. Now, I also asked on a YouTube community post and on my Instagram stories yesterday what questions you all had after seeing this image. You know, the kind of things that you still didn't understand that me looking at it with an expert eye would almost take for granted that was known, but actually that wasn't obvious at all. So the first of those was quite simply, why is it orange? So this is a false color image, right? We're not recording like orange visible light that we could actually detect and see with our eyes. The telescope is recording radio light. What it's essentially doing is saying, okay, where is there and where isn't there light in this region of sky? So the raw image is essentially like black and white. The problem is showing this image in black and white, the human eye actually isn't very good at picking out detail in a grayscale image. Like, it can't detect the difference between a bright region and a really bright region when you're just going from black to white. So they use a different color scheme essentially to show off this image. Now, you could literally use anything to represent the intensity of the light changing, right? You could use a rainbow, you could use red to blue, or this sort of black through orange through white color scheme that they've used here, which has sort of been the default, like the mainstay for a number of years now for any astronomical image that's taken at wavelengths longer than red visible light. So the wavelengths that are longer than we can actually detect with our eye, the likes of the infrared, the submillimeter, and radio light like this image here. It's also why James Webb Space Telescope images also have this similar orangey color scheme as well. They're also false color because they're taken in the infrared. The second question a lot of you had was, what are the 3 blobs? And why is there only 1 blob in the M87 image, but there's 3 of them in the Sagittarius A-star image? All right, so the blobs are what are known as hotspots, essentially where you've got these big clumps of gas in this ring of material that's orbiting around the black hole, that because there's more material there in this big clump, they will glow brighter. But if you remember, the material that's orbiting around Sagittarius A-star is doing so at incredible speeds, and it only takes, less than half an hour or so to go around. So if you observe it for a number of hours, every single night in a row for 3 nights, the location of that hotspot is going to change, so that when you average all the light that you've collected, you average all of those images, you're going to see it a number of times. You can tell, though, that one of the blobs in the Sagittarius A-star is brighter, though, and this is due to something known as Doppler beaming. Essentially, the light is brighter where the material is coming towards you as it spirals around the black hole. Think about a lighthouse beam, for example. Think about how bright it appears when it's pointing in a different direction, and then how bright it is when it sweeps around to point directly at you. It's pretty much the same thing here, except the effect is exacerbated by the fact that you've also got the material moving at close to the speed of light as well, so it makes that beaming that much stronger. But what it allows us to do is essentially work out, well, how is the material moving around this black hole? So for M87 star, it's likely that material is moving towards us like this, whereas for Sagittarius A star, it's likely the material is looping around the black hole like this. The third question I saw a lot of you asking was, what angle are we actually viewing this from? So the event horizon of a black hole is a sphere, right? Because we started with either a star that was a sphere or a big clump of gas that was a sphere, right? And we've collapsed it down till it's dense enough that we can no longer get any light from us, and that event horizon marks that point, which is a sphere, which means that we look at it from all the different directions, it's going to look exactly the same. But the thing is, it's also spinning, which means any material that comes into that black hole is essentially going to get flattened out into a big disk that we call an accretion disk. In the same way that if you take a ball of pizza dough and throw it above your head, it will flatten out into a nice pizza-based disk shape. So even though the black hole being like spherically symmetric, the same from all angles, the accretion disk, right, will have this flat plane that you can either see edge on or you can see face on. So you would think that it would look slightly different depending on what angle that you viewed it from. The thing is, because the black hole plays tricks on you because of the way that it bends light around it, we actually see almost the same view no matter what angle we look at this big disk of material around the black hole from. Almost, anyway, because one thing that does change is the locations of where that blob of material is the brightest that's coming towards you that gets Doppler beamed. Now, I know a lot of people thought that we'd be seeing this edge on because they assumed that, well, the axis that the black hole is rotating around and the axis that the Milky Way is all rotating around would be completely perfectly aligned. But in fact, we don't expect that at all. In the majority of studies that have been done on this, that have looked at sort of the spin axes of black holes versus galaxies, we actually find that they're completely misaligned, at least in the areas that we can get at this information. So usually we find this from the fact that the regions around the black hole, that material has been funneled into jets that have essentially come out of like the north and south pole of the black hole. And then you can figure out, okay, well, how is the black hole rotating? And we think that's because if you have a galaxy merger where both of those galaxies have a supermassive black hole at the center, eventually those two supermassive black holes will merge. And if they've come in at different angles, then essentially you will sort of average out the two different axes that they're spinning around, and you'll get something that's misaligned with the galaxy that's left over. Now, we have some idea over the axis around which M87 star is spinning, because M87 has these huge big jets coming out of it. And that's actually really helpful to know because it makes filling in those gaps where you don't have the data covering the entire image that much easier if you know what angle that you're looking at it from. The thing is, we don't know what angle we're looking at the Milky Way's black hole from because it's nowhere near as active as Messier 87's black hole. It's nowhere near taking in as much as material, which is why it's a lot fainter as well. Again, because we didn't know that angle, it's another reason why the image of Sagittarius A star is a lot more blurry than M87 star's final image. But the final image that we do end up with of Sagittarius A star is actually still really useful to help us constrain, okay, what angle are we actually looking at this from? You know, from the location of the blobs and which one's the bright one and how is the gas moving with respect to us. It can help us rule out certain scenarios. So the Event Horizon collaboration team, in all the papers that they published along with this image as well, essentially ruled out that we are looking at the disk edge on at 90 degrees. In fact, they actually managed to put a limit on it, saying that we have to be looking at it with an inclination of less than 50 degrees to us. And actually the most likely model has an inclination of about 30 degrees to our line of sight, looking directly at the black hole. So essentially the black hole is spinning at around about 60 degrees relative to the axis that the Milky Way is spinning around. Now, even though by studying other galaxies, we've seen that you can get all sorts of different alignments of galaxy spin and black hole spin, there still was sort of an assumption that in the Milky Way, the black hole spin and the galaxy spin would be aligned. And that's because of something known as the Fermi bubbles. We're not 100% sure what these are, but the best hypothesis is that they are echoes of essentially a big black hole burp that Sagittarius A star gave off at some point in the past. And from where we observed them in the sky, we figured out that they are perfectly above and below the Milky Way's disk, suggesting that when it was given off in this burp from the black hole regions, the black hole was aligned with the Milky Way's spin axis. So has it changed since then? So then you start thinking about ideas, well, okay, maybe the Milky Way has had a galaxy merger in the past, and that means that the black hole has recently merged, which perhaps changed the axis that it rotates at. Or are we thinking about the Fermi bubbles wrong? Perhaps instead of being sort of above and below, being expelled from the top, maybe it was expelled spherically, but the only reason we see them is where they sort of escape the galaxy disk, which is above and below. So there's loads of questions been raised by this inclination and figuring out what angle we're seeing Sagittarius A star from. So not only does this image prove that at the center of the Milky Way is a supermassive black hole 4 million times the mass of the sun, you know, rather than like a swarm of lots of smaller black holes or just like a clump of dark matter, as some people were suggesting in the past couple of years as well. It also lets us delve into the history of the Milky Way and the history of the Milky Way's supermassive black hole as well, and sort of ask questions about how the two have co-evolved, grown up together over billions of years. And finally, you all wanted to know whether we can also look at this with the James Webb Space Telescope. Yes, there are plans to look at the galactic center with JWST. I actually talked about this in my last video listing my top 5 targets for the James Webb Space Telescope if you want to check that out. But JWST will not be able to see this. It'll just be a blob. It's too small for Webb to resolve. Webb is much smaller than the EHT, right? It's only 6.5 meters across rather than the size of the whole Earth. The smallest thing that JWST can see on the sky is 0.00006 degrees, whereas the size of that glowing ring of light in the EHT image is 300 times smaller than that. Instead, JWST can peer through all the dust towards the center of the galaxy and reveal the stars orbiting around the supermassive black hole, and also any gas that's orbiting around the supermassive black hole just further out from the stuff that we're seeing in the EHT image. The proposal to do this was successful, so this is definitely going to be observed in James Webb's first year, and these observations will allow us to answer questions like, how old are all the stars in orbit around the black hole, and did they form there? Have they been affected by being so close to the black hole? Like, have they had their outer layers stripped? Is there actually maybe a collection of smaller black holes just orbiting around the supermassive black hole as well? Or maybe even like a big clump of dark matter that's stuck in orbit around the black hole as well? And once again, test predictions of Einstein's theory of general relativity, i.e. do we understand how gravity works, to extreme precision, more than we were ever able to do, for example, with the Keck telescopes, which is what Andrea Getz and Reinhard Genzel won the Nobel Prize for back in 2020. In the same way, the Event Horizon Telescope collaboration were able to test with their image whether the gas was moving very, very close into the black hole. Again, how we'd expect given what general relativity tells us. And they found that just like with M87, the gas is moving just as we'd expect. So once again, us astrophysicists find ourselves saying that even 100 years later, Einstein was right. Again. All right, those were the top 4 questions that I saw asked the most across my YouTube community post and on my Instagram stories. But if you still have a question that you're like, I still don't understand this about this thing in the image that you haven't found covered anywhere in any of the media coverage that you've seen, drop it down in the comments below and I'll see if I can answer it either there in reply or maybe I'll even make a YouTube short about it as well. So look out for those. But for now, roll those bloopers. All right, so the second question that a lot of you had were, what were these 3 blobs in the image? And why does this one have 3 and M87 only has 1? So these blobs are essentially what's known as hot pots. And so, hot pots. Hot pot. Oh, I'll have a lovely lanky hot pot for my tea, thanks. Americans are going to be so confused. And finally, you are wanting to know whether the James Webb Space Telescope would actually look at the galactic centre. Yes, there are plans for JWST. I've said it so many times. Come on, Becky. In a minute, I'm gonna need a picture of a black hole to pump me up.